whenever you're ready.
Am I sharing?
Yes.
Okay. Yeah, thanks, Young. Um, we'll be talking about these unentangled eigenstates in a central spin model, or as we'll call them, dark states. Um, so I'll first introduce the model, and then we'll get to the eigenstates of the model via a supersymmetric construction, and then to obtain the um, explicit eigenstates, we'll need to um, resort to the algebraic beta ansatz via the classical R matrix formulation. And then lastly, we'll get to the special eigenstates, which are unentangled to the dark states. So firstly, the model. So the model consists of a central spin labeled by 0, and then a set of Barth spins forming the environment, which only interact with the central spin via these XX-YY interactions. So note in this case, we call it a XY model because the X and the Y interactions can be different, and we have no ZZ type interaction. We also can apply a magnetic field on the central spin, um, indicated by these B terms. The model is integrable if the interaction coefficients satisfy this relation. So y squared minus x squared is equal to some constant, where beta here is called the anisotropy parameter. So if beta is 0, then we just get that the y and the x coefficients are the same, and we just get the more simple, more simpler XX central spin model. We also note that the central spin has to have spin half. The spin 1 case is also integrable, but we won't discuss it here, while the Barth can have arbitrary spin. We will use this particular parameterization for the interaction coefficients. So in terms of these epsilon parameters, so the x will just be root epsilon minus beta, and the y will be epsilon plus beta. Now, onto some physical applications and the motivation for the model. So one example of a system which it describes is a nitrogen vacancy center. So here we have a diamond atom, so consisting of carbon atoms, and then we take out one carbon atom, which gives us our vacancy, and then the neighboring carbon atom is replaced by a nitrogen atom, giving us our NV center. And then this acts as a effective spin particle interacting with the surrounding carbon nuclei and possibly a sample for which we would like to measure the magnetic field. So this can then be used as a very precise magnetometer by simply measuring the intensity of this NV center. Another system is quantum dots, in which it describes the hyperfine interaction. And then lastly, a more technological application is in quantum memory. So here we'd like to store a qubit possibly on say, the central spin, and then we want to be able to keep it in that state, not be perturbed by the environment. So that would require the state to be a product state. And then later we want to again couple this environment and the central spin to be able to read out that qubit. So that's the motivation for these unentangled or so-called dark states. So next we'll get to the eigenstates. So the key thing of key thing to realize with this Hamiltonian is that we can write it in terms of the supercharges. So they square to zero and they are just the Hermitian adjoints of each other. So then if we square the Hamiltonian, then up to a constant shift, it will just be equal to a supersymmetric Hamiltonian. And from the specific form of these supercharges, these will just be diagonal in the central spin Z eigenbases. So from these two properties, so firstly from supersymmetry, we know that the eigenstates will be, will be singlets or doublets. And from the diagonal property, we know that these can be, the central spin component can be taken to be either up or down. So for the singlets, these have the Bath component killed by both of the Bath supercharges, so T plus and T minus. And then for the doublets, they are just interrelated by these T plus and T minus operators. So a T plus sends a psi up to a psi down and vice versa for the T minus. So I guess the key property to realize from this is that if we apply, say, a T plus and then a T minus, then we get the same state back up to some factor. So that means that these states are all eigenstates of the T plus, T minus, or T minus, T plus operators. So now getting back to the Hamiltonian, we can directly construct the eigenstates from these. So firstly, from the singlets, we immediately have that they are also eigenstates of H, just because, just because the singlets are killed by the supercharges and they are diagonal in the SZ naught operator eigenbases. And then for the bright states, we simply have to diagonalize this system, giving us these entangled states. So I guess in contrast to the dark states, these will be referred to as bright states. Now, we mentioned that the doublet states generically exist for supersymmetric Hamiltonians, while the singlet states only happen when certain special conditions are met. So we found that if the magnetic field configurations take these values, then we will be able to obtain these singlet states. And only in these field configurations do we get these dark states. So now we'll head on to actually constructing the eigenstates. So recalling, we want to find the eigenstates of the T plus T minus operators. So these states. So the way we go about this is we realize that T plus T minus can be written in this form. So up to a constant, they are just a weighted sum of charges from what's called the XYZ Gaussian type model. So this is in the family of well-known integrable spin models with these long range interactions. So in this case, we have a quite general form where we have these self interactions and the interactions between the XX, YY, ZZ interaction coefficients are all different. Um, and the main feature that allows us to diagonalize these T plus T minus operators is that these charges were recently diagonalized by Skripnik using the algebraic beta ansatz. So we can directly use those results to find the eigenstates for these operators and then obtain the eigenstates and specifically the dark states for the central spin model. So next we'll briefly look at how the algebraic beta ansatz is done and how one obtains these charges via the classical R matrix. So the charges are obtained from this R matrix, which acts as acts from C2 tensor C2 to C2 tensor C2. And we get the magnetic field components from what's called the shift element, which simply is an operator from C2 to C2. And um, the generalized feature of this model is that the R matrix is not skew symmetric, in contrast to the classical Gaussian models, and instead satisfies what's called the generalized classical Yang-Baxter equation. So we have this minus here and then a swap in a sense. So these indices refer to like the Yang-Baxter R matrix, which sides the R matrix acts on non-trivially. And for the shift element, we get that it satisfies these commutation relations with the R matrix. Now, to actually obtain the charges, like I guess, say the Heisenberg model, we usually use a transfer matrix. So, and we get the transfer matrix from a Lax matrix. So in this case, we define the Lax matrix using these Lax algebra generators labeled with X, Y, Z. And these satisfy these commutation relation. And so noting the form of this equation and the form of the generalized classical Yang-Baxter equation and the shift element equation, we immediately get that we can get a solution to this equation, so a representation of the algebra from the classical R matrix and the shift element. And then from these, we can then construct our Lax matrix simply by taking the tensor product with the Pauli matrices. And then lastly, we get to the transfer matrix, which will just be the trace of the square of our Lax matrix. And it takes this nice form where it's just the square of the generators, the square sum of the generators. So to guarantee integrability, we want that these transfer matrices commute for different spectral parameters, and that holds here, basically coming from the um, algebra relation satisfied by the lax generators. And then again, like for the Heisenberg model or the other integrable systems, we can obtain our charges or the Hamiltonian, in this case, by taking the residue at one of those epsilon parameters of the transfer matrix. So we get this form. So the shift element, like I said before, gives us the magnetic field components. We get the interaction coefficients from the R matrix, and then uh, simply from the regular part of the R matrix, we get the self-interaction terms that we saw. Now, to actually diagonalize the transfer matrix and obtain the eigenstates, we can first write the Lax matrix in this 2 by 2 matrix form, so that we have these diagonal operators and off-diagonal so-called raising operators. And then we simply take a reference state to be a lowest weight vector. So it will be killed by the lowest, the so-called lowering operator, and then it will be an eigenstate of the diagonal components. Now, in this case, for this model, the ladder operators, so the raising operators, do not commute. So that means that if we construct our state by multiplying these ladder operators successively onto the lowest weight vector, the order will matter. So we'll get different states depending on the order we apply them in contrast to what we would want in the usual algebraic beta answer. But this can be relatively easily overcome by simply shifting our raising operators by some constant. And then if we define the beta state in this way with the shifted with the shifting, then the state won't depend on the order of these spectral parameters for the beta state. Then lastly, to obtain the actual eigenstate, we simply apply the transfer matrix to this beta state, and then use the Lax algebra relations to commute through, so that we can apply, say, the lowering operator and the diagonal operators onto our lowest weight vector. And then that will give us basically the state back along with some unwanted state, and then requiring that those unwanted states are zero, we have to apply certain conditions on these spectral parameters, which will guarantee that it is an eigenstate. So these are known as the beta ansatz equations, and then the solutions to those equations will be the beta roots. So now coming back to actually constructing the eigenstates and the dark states of the central spin model, we remembered that we wanted to get the eigenstates of t plus t minus and t minus t plus. And so if we notice that these can be directly written in terms of our lowering raising operators, C and B, we can simply use the algebra relations to apply these to our beta state. Sorry. and commute through to obtain this. So then we will get an eigenstate from this. Firstly, say if one of these u parameters was equal to beta, then we'll get this eigenstate with its eigenvalue, setting the rest of the terms equal to 0. However, we also would need that this term has to be 0. The second case is if none of the roots were equal to beta. And then in that case, for this to be an eigenstate, we require this to be 0 and this also be equal to 0 because none of these states have the form of the eigenstate. So in both cases, we see that we need this term to be equal to 0. And this condition simply corresponds to the magnetic field term satisfying this, which we saw at the start was basically the condition for dark states. And so we see that we obtain two eigenstates at when this condition is satisfied. One when none of the spectral parameters are equal to beta. So for these, we have a 0 eigenvalue, and so these will be the singlets. So t plus t minus acts onto our state as 0, which, remembering that t plus and minus were Hermitian conjugates, means that both t plus and t minus will kill our state. And then the second case was when one of these parameters was equal to beta, and this corresponds to our doublets where we were basically swapping between the up and the down states based on the action of the t plus or the t minus. So the first then gives us our dark states. And as we see, these will only occur when the magnetic field satisfies this equation. Now, it's important to note that this beta ansatz has to be further modified if this condition doesn't hold. So this isn't 0. So in that case, we still obtain these doublet or the doublet states giving us our bright states. However, we don't get these singlet states. And to show that that really is the case, we'll give an alternative construction. So firstly, firstly recalling from the supersymmetry that our eigenstates were only the singlets or doublets, and the ones coming from the doublets took this form. If this was a product state of the central spin and the bar state, then that requires that this component, this component will have to be proportional to this state. And if that is the case, then that means that the psi plus and psi minus states have to be eigenstates of both of the charges. And if they eigenstates of both charges, then they certainly also eigenstates of the difference, so also of the SZ operator. But this will just mean that the eigenstate will simply have all of the spins up on each of the sides. But if we simply take, say, the x component of the magnetic field to be very large, then we can see that these aren't actual eigenstates of, say, the Sx operator. So this is a contradiction. So the only possible states which are product states or dark states are the ones coming from the singlet states. Now, let's construct those. So recall that the singlet states had this form where the A plus or minus killed the state. Sorry, I guess this should be a t plus or minus. And then we first rewrite our operator in terms of the plus and minus operators. And then we can define these operators, basically the SL2 operators. So we get some representation of the SL2 algebra. And then with this, we can rewrite our, say, T plus operators using just the diagonal or Cartan elements of SL2. And we can just diagonalize A plus with these eigenstates. So immediately we will get what the eigenvalues are. So just, I guess this is the lowest weight vector state killed by the lowering operators. And it's a diagonal with respect to the Cartan elements. So doing all of that, we just get these eigenvalues. And then recalling that for these to be singlets, these eigenvalues have to be 0. And then this really just corresponds to this condition, which was the condition we saw before using the algebraic beta ansatz. So that finishes my talk, and these are just some of the references going into the research. Thank you.
Um, hmm, so, well, let's thank Jaco. And um, are there any questions for the speaker? If not, then I have a, well, relatively naive question. So if you go back to the first few slides that talks about the eigenstates. Yeah, I think it's here. So the phi and psi, singlets and doublets or dark and bright states. Just wondering why they get these names, and like what exactly are they how exactly are they different?
Yeah, so I guess they come from basically the um, the eigenstates of a supersymmetric Hamiltonian are either um, pairs, come in pairs related by the T plus. So really, I guess T and T dagger in a sense, related by those operators. Or the only other possibility is if T acting on the eigenstate gives 0, so those being the singlets. So I guess doublets meaning doubling, so they come in pairs, or singlets, there's just a single one of those. I guess that's where the naming comes from.
Yes. Mm, Thank you for the answer. Um, are there any further questions? If not, let's thank the speaker again. Um, and thank you.